Okay, welcome to the video lecture on the second part of chapter 5. In this video, we're going to be going over a lot more examples about interactions between objects, especially ones that involve friction. And we're also going to take a closer look at how tension is going to be working in a lot of our problems. So when we have things that are connected, if they're not touching each other, like if the last example we had from the previous lectures, we have these two blocks that are touching each other as they're sliding down an incline, and so that's how we deal with their interaction. Well, a lot of situations have um, blocks being connected because of, say, a string or something, and so we want to make sure we understand how we're going to handle that. And there's some simplifications that we make when we deal with strings. So what you should assume, unless you're told otherwise, is that if you have strings or ropes or something like that that connect objects, that they will be massless. And what does that mean when we say that they're massless? Well, that means you don't need to do a free body diagram for them. You don't need to be concerned about the motion of the string. You simply have to realize that there's a tension that acts on the two objects that are connected by the rope or the string, and you can treat those two tensions as a action-reaction pair. So as seen in the figure here, if these things are connected with a rope, we can basically ignore the fact that there's a rope there, and we just simply say that there are equal and opposite forces as a result of the tension. Now be careful though, because on the homework that I will assign, there will be ropes that will have mass, and so you can't make that assumption, and that means you will need to do free body diagrams for those. All right, so let's just jump right into a problem. This is very similar to the problem I did in the previous lecture. The only difference is that we have this tension that connects the blocks. And if you look at the coefficients of friction here, we can see that the lower block has a lower coefficient of friction and the upper one has a higher. And that's important because that means the lower block should slide down the ramp at a greater rate than the other one, simply because it has less friction. If they were coefficients of friction were equal to each other, then there would basically be no tension because they would slide down at the same rate. And of course, if the one on top was higher, it would eventually run into the other block. Sorry, I'm sorry if I said that right. If the upper block had a lower coefficient of friction than the bottom block, then it would eventually catch up and run into the lower one. All right, so let's look at how this problem is done. So that's right here. All right, so as always, free body diagrams. I'm going to call the upper block block 1 and the lower block block 2. And so we have a ramp angle of 20 degrees. That means there's gravitational vectors that are at a 20-degree angle with respect to our tilted y-axis. So FG1 on block 1, we have a normal force that is going perpendicular to the incline. I'm going to call that N1. We got a kinetic friction up the incline, and then we have the tension, which is down the incline, that is pulling that block down. And so now, in this particular problem here, I noticed in my free body diagram, my tension T2 on 1 does appear to be a little small. That vector length should be probably a bit bigger, or the friction is smaller. But anyway, the block is accelerating down the incline, and down the incline is positive. All right, let's go to block 2. We have gravity down. We got our normal force, N2. We got the tension 1 on 2. That's the Newton third law interacting pair with the tension in the other free body diagram, and then this friction kinetic up the ramp. So those are all the forces that we are working with here. And so I connected the Newton's third law interacting pair with the dashed line there. Again, the only issue with this is I noticed that tension T2 on 1 probably should be a larger vector, or the kinetic friction one should be a smaller vector. Anyway, let's go to Newton's second law. So with Newton's second law on block 1, so we have our normal force upward. We have a component of gravity that is perpendicular to the incline. So we're using the cosine there, and that sums to 0. The forces in the x direction, we got tension 2 down the incline, that's positive. The component of gravity that's down the incline is positive, and then the kinetic friction is negative. We set it equal to m1a. The exact same treatment happens on block 2. Okay, so you'll notice everything about that is the same. The only difference in Newton's second law for block 2 is that the tension there is negative because it goes up the ramp there. Okay. Now, because the tensions are, Newton's third law, then we can just call them all the same thing. We're just going to call them T. And so you solve this system and it will give you a tension of 0.61 newtons. Now, just to be clear about how you're going to solve that, in the y equations, you solve for the normal forces. The F sub k's become mu sub k times n, and you plug in the n's that you get from the y parts. And basically what you can do in this problem here is probably divide both equations by the mass so that you have equations that are equal to the acceleration. The accelerations have got to be the same. So the accelerations being the same. Hi, Scout.
What are you doing?
I'm busy. I'm doing a lecture, Scout.
What are you doing in the ice room?
Yeah, well, I have to record my lecture in Iris's room.
I want to play in ice toys.
Okay, well, I'm busy with the lecture though, so you have to go see Mama right now, okay?
But I want to play with ice toys.
Okay, back to physics. All right. Anyway, what was I saying here? Okay, you probably just want to solve for the acceleration of both the x equations, set the the statements for acceleration equal to each other, solve for t. It's a bit of algebra, but no big deal, right? Okay, let's get back to the PowerPoint. Okay, so in this question here we have boxes A and B are being pulled to the right on a frictionless surface. Box A has a larger mass than B. How do the two tensions compare to each other? So what you're looking at here is you got a tension between blocks A and B. We got tensions between block B and whatever's pulling things to the right here. So think about this question for a moment. And the answer here will be C. So tension 2 will be larger than tension 1. Now, one thing you don't want to do here that I see a lot of students make a mistake on is they want to make the tensions all the same. And that's true when you have one continuous piece of rope. So, for example, in tension 1, whatever tension's in that rope, that's continuous all throughout the rope, it's the same. And same thing with tension 2. The tension is continuous all throughout the rope, again, because they're massless. If they have mass, that is different. But the way you should understand this problem is that tension 2 is pulling 2 blocks, and tension 1 is pulling 1 block. So there would need to be a greater force on tension 2 to pull the 2 blocks. All right. So this brings us to another part of interactions where there's things in contact, and that's what's referred to as acceleration constraints. And this is something that is a more challenging aspect of when you do Newton's second law, because how you state your accelerations needs to be done manually to some extent. For example, if you know your object is accelerating in a negative direction, you have to make sure that you put a negative sign in front of the acceleration there. But some accelerations are really simple. I mean, like if you go back to this example here, the acceleration constraint here is that we have two objects that are accelerating and their accelerations are equal to each other, and they have to be. If they were not equal to each other, then there would need to be no tension because block 1 is moving faster than block 2, or the rope would have to stretch or break because the top block is not accelerating as much. So there's a constraint here in that the accelerations are equal, right? Same thing with this problem here. The accelerations have got to be equal here. In the example of the car and the tow truck here, the accelerations have to match, right? If they don't match, then again, the rope stretches and breaks, or the tension's gone and the car runs into the back of the truck. Sorry. So while we may want to label accelerations differently, because we label like forces differently depending on what object they're on, for accelerations, just call it A. So, right. Now, this one's a little trickier. And so when we're actually considering both, Newton's third law for this and the acceleration constraints, the string is massless here. The pulley, we also make some assumptions about that pulley too. The pulley is considered to be massless as well. No friction on that pulley. And so what we're saying with that is that there's going to be no contribution from the string or the pulley to any free body diagrams. The ropes are simply connecting the two up, right? And the tension is continuous throughout the string because it's one continuous piece of string. The acceleration constraint here, though, is what's stated at the bottom here, that the block A is going to accelerate to the right, so we'll say it has a positive acceleration. But block B accelerates downward. Now, if we're going to call down negative, which we normally do, then that acceleration would actually be negative, so we have to actually manually put the negative sign in there. Okay. Also, if you look at the free body diagrams for these blocks here, you're going to have your tensions are not going to look like equal and opposite forces, because a tension's going to the right and then a tension on block B is going up. But again, because of the massless approximation, we treat them as if they are that. Okay. By the way, if you're interested, a more realistic situation here would be that we do have to consider the pulley. We do a free body diagram of the pulley. The pulley has probably a mass to it. There's a moment of inertia, and so that's going to be part of the system, which, by the way, we will be doing when we get to the sections on rotational motion. We're going to revisit these problems, and our pulleys and our strings will have mass, and we have to consider them. But fortunately, the easier way to do those problems is with energy. So you'll see that when we get to it at some point. All right, so let's consider what's going on here with the acceleration constraints. We got these two blocks connected by a rope to this pulley here, and we are making the assumptions here that the pulley and the mass and the strings are massless. Block A is the heavier block, so the answer here would be C. So block A is going to be accelerating downward, and block B is going to be accelerating upward. So one of them needs to be negative. I mean, it really doesn't matter which one you choose. When we say C, we're simply identifying the fact that one acceleration is positive, one acceleration is negative. So specifically where you put the negative sign is really of no consequence here, mathematically. All right. So, in fact, I think this is what I was just talking about before, but this kind of illustrates the point I was making in a couple slides ago, where the picture on the right is the more realistic situation when you consider the pulley, because we have the two tensions and we have this force that kind of points up and to the right that balances the tension forces in the pulley, and then you may have to treat the pulley as a separate object and deal with that. But the simplification here is that entire free body diagram for the pulley is just gone, and the TS on A is going to be equal to the TS on B. Right? So that's what we deal with there, which is what's shown right here. And so this would be the nice free body diagrams of this particular setup here. So note the vector lengths, because there's going to be an acceleration here, assuming no friction. But this is a really good look to this situation here. All right, so now we want to just think about how things are connected. So in this problem here, we're considering a 50 kilogram block that's being hung by the rope, and we have these two 50 kilogram blocks that are connected by this pulley here and a rope. So what do you think is going to happen with tension 2 here? So think about that for a moment. And the answer here is B. So the tensions have got to be the same in these two. And, obviously for the one on the left, the tension's got to be equal to the weight of the 50 kilogram block, because that's what it's supporting. And, for individually the blocks here, we have tensions supporting both of these objects. But if you look at their free body diagrams, they really have to be the same, because this pulley's not going to move. I mean, if it's kept at rest initially, it will stay this way. If you give it a little kick, though, yeah, it's going to start to move at a constant speed. But, some students obviously think that, block, the rope for number 2 has to be 100. It has to support the weight of 100 kilograms. And that's not true. There is something supporting the weight of 100 kilograms, and that's the connection of the pulley to the ceiling. That is supporting the weight of 2 blocks. But individually, the strings are supporting 50 kilograms. All right, so let's think about what's going on in this situation here. Table is still frictionless. The mass is falling, and we want to determine what the tension in the string is here. So think about that for a moment. The answer here is A. All right, so why? Well, a free body diagram of block M would have mg down and tension up, but because there's no friction on the top block, this system is free to move, and that means it has a net force downward. So that means the tension will need to be less than mg to have an F net that is down. Okay, great. All right, so we have a similar situation here. We got a block that's being hung here with has a weight of 10 newtons. And then the situation on the right is a very similar situation, except the block is not there. Instead, there's something that's producing a 10 Newton tension going down, and we want to determine what's going on with the situation. So think about this really hard. You may want to pause the video to ponder this for a bit of time, but here the acceleration is, the answer is going to be C. Okay, so block A is going to accelerate slower in case A than in case B. Okay, well, what's going on here? Well, if you look at, the free body diagram on the 10 Newton block on case A, it's what we just did in the last question. It's got a tension up that's not as big as the weight that's going down. Well, what's going on with case B? Well, the best way to understand this is there's no free body diagram for a block that's hanging. It's just a tension that's downward. And what that means is the amount of mass in case B is overall less. So actually, this is kind of combining, a couple questions we had before here. The way you can sum this up in the most succinct way is to simply say, well, case B has less mass. So the same force, okay, would be producing a higher acceleration, right? Because if we look at that case A also, it's 10 newtons going down, right? But the tension going up is less. So the F net is different there too. But that's ultimately due to mass. So, there's less mass in case B. The F net going downwards different. So, having a mass there, not having a mass there actually does result in a pretty different outcome. All right, so let's work on this problem here. This involves kind of everything we're talking about here. We got friction, ropes, pulleys, inclines, got it all. All right, so what do we do first? That's right. Everybody's head, you said free body diagram. Well, good for you. And if you didn't, well, I'll just assume you did. Let's look at that. Where is it? Okay. Wow, this is crazy, huh? All right. Just go real slow through this then. All right. Free body diagram of mass 1. Mass 1, all right, is this one that's on the incline. So I got a tilted coordinate system. I got gravity down, Fg1. I got normal force up perpendicular to the incline. I got my tension up the incline, and I got max static friction here. Now, why do I have max static friction here? Well, the question asks, what is the minimum mass that will stick and not slip? All right, well, not slip. That means static friction, and what we're trying to consider here is, being at that maximum value of static friction. So, so we have our F max, because what happens is the block would like to go up the incline if it could. Okay. All right, now before we actually get in to what's going on with the second block, let's actually just pause for a minute here and just think conceptually about what's going on with this mass here, right? Because there's a lot of scenarios that can exist, right? One scenario is, what if the mass is super small, right? Super, super, super small. Well, then that means the 2 kilogram block that is hanging there is not going to have much of an issue moving that block. You're going to very easily overcome static friction, and the system is going to move. So then you start to up the mass. And as you start to up the mass, then what happens is the value for the max static friction is going to start to go up too. And then at some point, the 2 kilogram block can't move it. And so it's going to be stationary there. But then what happens if we keep going, right? We're going to keep going, keep going, keep going. At some point, the mass of M1 is going to get really big. And then it's the one that can start the motion. So at some point, the mass gets very, very large, and then it can overcome its own static friction, and then the whole system moves down the incline and the 2 kilogram block goes up. So that's just conceptually what's going on in a situation like this. This particular problem, we're sort of interested in, what's that small mass that you can up a little bit until things start to move. So that's what we're considering here. All right, free body diagram for block 2. Nothing's moving right now. Tension's up, gravity's down, they're equal. Okay, so below that are our Newton's second law equations. Okay, for block 1, we got our normal force, and we got the component of gravity that is perpendicular to the incline, that's set equal to 0. We got a minus max static friction plus our tension. Gravity goes down the incline, so it's negative, and there's a sign function there to indicate the component that is down the incline. And we're setting it equal to 0 because we're not accelerating at the moment. All right, block 2, we got tension, and we got our gravity. That's set equal to 0, so we can see what the tension is. The tension is m2g. So that's going to go into equation 1 over here, right? So we're going to put m2g in there. The max static friction becomes mu sub s m1g cosine theta. Why? mg cosine theta is the normal force. So this max static friction is mu sub s times n. Well, we know our n from from the y equation here. So now we got this equation down here, and we can solve for m1. You're going to have to group terms here, right? In fact, looks like the best thing to do is probably move these two negative terms to the other side. Now everything's positive. You can factor out the m1, divide by the stuff that's multiplying it, and we end up with a mass of 1.8 kilograms. So what does that mean? That means if you're under 1.8 kilograms, then things are going to be able to move. But when you get to 1.8, now we're stuck here. And if you keep upping it, we're going to be stuck still. And at some point, you can change this problem around and say, okay, well, let's see what's going to happen if we start to move a bit. Okay, but anyway, you got to remember what we did from last lecture here. Was it last lecture? Yeah, the one friction in it. So if we nudge a system, that means we're allowing things to move. And so what happens here, we're forcing movement. So the max static friction converts immediately to a kinetic friction. And since we are at the max static friction, the kinetic friction is always less. And so the forces that are involved in this problem will be able to move the system because the requirements to move is less for kinetic friction. So, we go to our Newton's second law because, this picture here is not really going to change much if we let things move. What does change? Well, the max static friction and now becomes a kinetic friction, and the vector should shorten a bit. And the free body diagram for number 2, well, we're now accelerating, so tension's gonna go down a bit here because we're gonna have our gravity pushing us down. So that's what you see here. We changed this to F sub k instead of F sub s, but everything else about it's completely the same. Now, well, sorry, we have an acceleration, right? So m1a, that's what we want to have here. All right, and this is part of our acceleration constraint that we talked about previously in the lecture. Here we have our tension, we have our gravity going down, but then we have a minus m2a, right? The block's going to go downward. I'm not using different symbols for a. It's the same accelerations, but the acceleration is negative, so I'll need to manually put a negative sign here. If you don't put a negative sign there, you will not get the right answer. In fact, if you put a negative sign there, you're going to come up with some weird situation where the second kilogram block accelerates upward, while the m1 accelerates upward too. That's a crazy world. It doesn't happen though. All right, we solve that system. Okay, just like you solve the system on the left-hand side, we get acceleration of 1.3. So incorporating kinetic friction is not really actually changing much in our problem. Here we just make a little switch. All right, great. Moving on to... All right, circular motion now. All right, so we got our frictions taken care of. We got our tensions and pulleys all taken care of. Now we can explore some more interesting problems, and the remainder, I believe, for the rest of this chapter is really focused on circular motion problems here. Now, if you remember from the stuff we talked about previously for circular motion, it can be translated to one-dimensional motion. I mean, technically it's two-dimensional motion. There's an X and Y movement on this stuff. But ultimately we can transform this into a coordinate system where there is only one direction here to worry about. And that coordinate system here it's like a polar coordinate system. It's not quite a polar coordinate system. Um, it's what's called an RTZ coordinate system. So instead of x, y, z, we got r, which points towards the center of our circle, right? And then we have t, which is the tangential component. So it's it's a tangent to the circle there. And we have z, which is our standard z. Now z is the direction that is perpendicular to the circle of motion, right? So the plane of motion is defined by the RT plane, and then z is above or below, right? Now, in our problems, what will not change? Z won't change, and r won't change. Okay, so the only thing we're considering here is t. Okay, and also you can also just take that t and translate it into a theta, and you do have like a cylindrical coordinate system that you could work with. But we just treat this as t for what we do in our physics problems here. So this is one-dimensional motion now. We only really consider what's happening with t. Okay. So, when we deal with things in uniform circular motion, there's an inherent acceleration that occurs there. So if we solve our problems with Newton's second law, if there's any kind of circular motion, then there will be an equation in the r direction. And that equation will have to include an ma with the a being centripetal acceleration. So remember again back at the end of chapter 3, we worked out that the centripetal acceleration is v squared over r or omega squared over r, right? There is no velocity in the r direction, right? There is velocity in the t direction, and that is what we refer to as the linear speed or the tangential speed, and that's omega r. We're keeping z stuff 0, and the tangential acceleration is 0. Again, that's required for uniform circular motion here. So, with this new coordinate system we have here, we think about Newton's second law, and that means we can sum the forces in the r, t, and z directions. And for the summation of forces in the r direction, we're going to always have an m v squared over r or m omega squared r, depending on what information we're given and what's more convenient for us to use. All right. Well, what is this? I don't think this is anything I haven't said. Yeah, you already know this stuff. Moving on. All right. So, the acceleration is due to a centripetal force. Okay. However, centripetal force is not a type of force. It is a form that forces take. Okay. So, for example, we've talked about forces like gravity and tension and friction. Those are types of forces, and those forces can produce many different types of motion, right? They can produce translational motion, rotational motions, circular motions, and so on. So what we will do is when we solve our problems that involve circular motion, we do not include a centripetal force as a force. That is no force. What happens is that forces that we already know about, like tension or normal force or gravity, will act as a centripetal force. So in our problems, when we do our free body diagrams and we consider r, t, and z coordinate systems, anything along the r direction will act as our centripetal force. And that's the form of that force, okay? But it's not the type, okay? So when I'm making that distinction here, types are the different names we give those forces, whereas form is the nature at which we apply them and analyze them, okay? So let me put it this way. When you do your free body diagrams for uniform circular motion, you're never going to label something as like F centripetal or F cent or what. No, you don't do that. The only thing that you really do that is different is you have this different coordinate system. You have to think about the forces along that coordinate system, and then you have an acceleration in the r direction. Okay, but there's no new forces here, right? No new forces. Okay, so we got a hockey puck tied to a string in the ice. And we think about how many forces on this. So think about this for a moment. You may want to pause to really ponder this. But the answer here is 3. Now, a couple things about this. You look at this and say, well, is there friction? Well, there's a couple ways to know that we're not having friction here. One vague way is to say, well, it's ice. Okay, and then you can say, well, there's a coefficient of friction for ice in my book here. Yeah, that's fine, but the ice is meant to indicate that things aren't going to be experiencing much or any friction at all. But here's the other way you know there's no friction is because all our problems are uniform circular motion. If there was friction, this wouldn't be uniform circular motion. There'd be an acceleration, and that's not what we're doing right now. Right? We're doing uniform circular motion stuff. So that's really ultimately why we know that we don't have any friction to deal with here. Not to say that friction won't show up in these problems. It certainly can, but not in this one. All right, so what do we got here? We got gravity down. That's 1. Normal force up. That's 2. And the tension that's pointed inward. That is 3. All right, so what are the directions there? All right, well, the tension is the R direction. The normal force is the, probably call it positive Z direction. Probably call gravity the negative Z direction. By the way, the R direction for tension is positive. You should always call toward the center of the circle the positive direction and away negative. That would be wise to do. And the reason why it's wise to do is because your accelerations always point inward, and we want to make those positive, right? Okay, there's no other forces that act here because you'd have to have another agent. And all we have is the tension and the ground here, and we've already accounted for what they're going to do. No friction, okay? No air resistance, something like that. All right, let's move on. All right, so, oh, I gave this away. Well, maybe you weren't paying attention 30 seconds ago, right? So think about this for a moment. I'm going to pause, but the answer here is D. Yeah, I really don't know how you think it's any of the other ones. No offense. But yeah, no friction. No force and gravity are vertical things here. So tension in the string is the centripetal force here. So we would label, in the 3-body diagram, we'd label that force T. And that would be equal to mv squared over r. Okay. Let's do a problem. All right, not so crazy here. All right, so here's my coordinate system. So just so you can sort of see, how I'm visualizing this, I am gonna draw this coordinate system as if my eyesight is like level with this table. Imagine it's a table here, right? My eyesight's level with the table, and so I'm watching this thing kind of move away from me as it's swinging around that circle there. And so what that means is the R direction is to my left here, and I've labeled the left with the R, so that's positive, and the right's negative. Normal force is upward, and that's positive, and gravity is downward. I'm going to call that negative. And the T direction, right, is in and out of the page. Okay, but there's nothing in the T direction here, so I'm not going to include that. But I have no T direction forces to worry about or motion that I'm considering here. So the only thing I really need to do is sum the forces in the R direction. I mean, I could sum the forces in the Z direction, but there really doesn't appear to be much use to that because normal is going to be equal to gravity, and that's all we have to work with here. And there's no normal force that shows up in the R equation. So it's simply tension equals mv squared over r, or you can say m omega squared r. In this particular problem, I think the m omega squared is better because omega is 2 pi t, and we have t, that's the period. So that's probably the easiest way to do it. If you want to do mv squared over r, you're going to have to figure out what the velocity is, which is not hard to do, but it's just an extra step that you probably don't need to do. So this is m 4 pi squared, tension squared, because the omega squared, r here, and then plug in all those values, and we get a tension of 3.9. All right. Now, notice a couple things here. Diameter, got to have radius. Centimeters, nope, never use centimeters. You will, don't worry, you will, but you shouldn't. And meters for everything, right? Kilograms, that's good. Kilograms are good. Seconds are good. Okay, so really pay attention for the units here. Okay, this is a simple problem, but 2 really common things to mess up is you got to use radii, and everything's got to be SI. Okay, meters. Right? Ooh, this is a good problem. All right, so we got a 1500 kilogram car moves around a flat 200 meter diameter. That's 100 meter radius. Circular track at 25 meters per second. What is the magnitude direction of the net force in the car? What causes this force? All right. Now, what is the max speed that the car can have and remain driving in a circle? Well, that's the second part of the question, and that won't make a lot of sense until we tackle the first part of the question. So let's tackle the first part of the question. Free body diagram. All right, here we go. All right. So I drew a picture here, which is going to act as sort of an overhead view of what's going on. We got our car. It moves in this circle, right? The diameter is 200 meters, so the radius is 100 meters. And I got my R direction here, and this would be the tangential direction. That's the direction of motion of the car, and the Z is in and out of the page. Now, I'm not really concerned about anything in the T direction here, so when I do my free body diagram, I've now taken this circle and put an edge on, and just like the free body diagram in the last picture, I'm looking at this with my eye level to the ground here, right? So this little arrow I drew down here indicates the direction I'm looking at the car for my free body diagram. So what do I got here? Well, now my normal force up, and I got mg down, and my force that's to the left. Okay, well, it's not a tension, right? There's no ropes here. So, you know, what kind of force is it going to be? Well, the tires are in contact with the ground. Okay, well, there's a normal force, right? But there's also a static friction. Now, why static friction? Well, here's the thing. Those tires are not moving in the R direction, okay, relative to the ground. They're also not even moving relative to the T direction, but we're not considering the T direction here. But it's just static friction, and it's preventing the start of motion. Because what should this car do if there were no friction? It would go in a straight line. So that means, well, that means several things, but one of the things that means is if it goes in a straight line, the value of R increases. So that means we have to have a static frictional force that points in the direction of the center of the circle to produce the acceleration that keeps us in the circle here. So this is a static frictional force, okay, static friction. It's not kinetic, okay? Remember, kinetic friction is not about if something moves or not. It's about how things move relative to each other, okay? The tires are not moving relative to the ground, okay? The point of contact, right, does not change when the tires in contact. If it did, it was going to skid. Anyway, all right. So it's static friction. That's what causes the force. So what do I got here? Well, I got a sum of forces in the R and the Z direction. Z direction is not very interesting here. It's just N equals mg. Static friction is to the right. I'm calling that positive, and this is equal to mv squared over r. This doesn't look like an equal sign because it's not, but it should be. So there's an equal sign right here, right here. And then I'm going to solve for the static friction, and I'm going to get 9,400 newtons. All right, so that's how much static friction is needed. Okay, now this next question makes a ton of sense. What's the maximum speed that the car can have? Well, okay, what's going on here? Well, this static friction grows with speed. Look, there's a t squared right there. Right, so the static friction grows. You go faster, you need more friction to keep you in the circle. Well, we know there is a max value for static friction. So the max value for static friction is mu sub Sn. And so we do need N now from the Z direction, that's mg. So we now have mu sub Smg equals mv squared over r. The m's drop out here. And we're going to solve for speed, I guess. Yes, we're solving for speed, so that's going to be mu sub S Rg in this equation here. Now, the mu sub S, this is a car, rubber tires, concrete, asphalt, whatever. The value is pretty close to 1, which is good because you want a lot of friction on a road or you're going to be slipping around a lot. And this speed here is 31 meters per second, which is, what's 31 meters per second? It's like 31 times 0.44, something like that. No, times. Oh, wait, no, divide. 31 divide 0.44, something like that. 70 miles an hour. Okay, I can believe that. 70 miles an hour going in a circle 100 meters. That's dangerous. Right, don't do that. Scout, no. I'm making my lecture.
Oh, yeah.
Yeah, go away. Thank you. Moving on. Oh, where am I? All right, here I am. Okay, so 70 miles an hour, not too fast, right? We want to go faster, right? We want to go faster on the road. just because we want to, right? A car turns on a road that's banked, right? Which of the diagrams could be the car's free body diagram? All right. Think about that for a minute. And the answer here is D. D. All right. So, okay, so the forces kind of grayed out here. All right, so what's going on here? What are these forces? Well, gravity's down, and we have our normal force that is up and to the left, and we have our static friction, right? So this is just like, the other problem, except we now tilt the coordinate system, so that means the normal force and the static frictions get tilted. And what do we see is going on here? Well, we see that we can provide a larger net force inward, because even if we're at max static friction, the normal force is now helping out, right? And that's the purpose of the bank roads. So let's talk about bank curves here. Okay, bank curves allow for forces more than the max static friction to supply a centripetal acceleration. And it's done with the normal force. So basically, the road pushing in on the car can supply a component of the centripetal acceleration. And it's based on how much you want to tilt that road there. But you got to have to balance that, because you tilt it too much, then you can overcome max static friction in the R direction, and the car can actually like slide down, right? So if you have a parked car on a slope, well, it could slide down in the R direction. Obviously, you're going to be going fast. That's not going to happen here. But anyway, so the value that I have listed right here, and I'll show this an example in a little bit here, but if you have a banked road of radius r, and the bank angle is just theta, then the speed at which the car goes when you don't need any static friction is going to be is equal to square root of rg tan theta. Okay, so that's if you don't need any static friction to do this, right? So let's look at situations where you do need it. All right, so here is a consideration you have to make if you go faster than that v naught speed. If you go faster, well, you're going to need more centripetal force to get you in that circle. So that means you're going to have a component of static friction that points down. Again, if you're going very fast, you're going to want to go in that straight line. And then so there's got to be a static friction that pulls you inward to do that. Okay, so for a speed that's high, you're going to have a static friction that's going to be downward, down to the left. Now, if you go too slow, then what happens is you have to have static friction go the opposite direction. Okay, why? Well, it's because going too slow means that the normal force is the normal force is not going to change here, right? It's based on the mass of the car and the bank angle. So if you go too slow, the normal force may be overcompensating, basically. It's too much. And so the static friction has to go the other way, and that prevents you from sliding down the bank. And again, if you park the car, that's kind of the maximum amount of that, right? So if you have any speed, those two are going to try to counteract each other, all right? Now, one other thing I want to mention about these problems, though, is you notice that these are not tilted coordinate systems, right? These are not tilted coordinate systems. Why? Well, we do have more than two forces. Sorry, we have two forces that are tilted and one that's not. And I've told you before, tilt your coordinate system to make your math easier. But that wasn't the only reason I told you to tilt your coordinate system. Makes the math easier, but what it also does is it makes sure that you get an acceleration that's in the direction you're traveling here. Okay, well, this is centripetal force. It's center secant. It's pointing towards the center of the circle, which is horizontal. Okay, if you travel on the bank road, okay, the center of the circle of travel is directly to the left here. So if we were to tilt the coordinate system, you're going to get an acceleration in a direction that you're not even traveling. It's not an R or a T or Z direction at all. And you're not going to get any answers from that. So in this situation here, we cannot tilt the coordinate system because we need to find the forces in R and the acceleration in R. If you tilt things, you don't have R and T anymore, or Z. You have nothing. You go back to X, Y, Z, and good luck solving that. So, all All right, so let's actually do a problem where we cover all this stuff. Oh, almost done here. All right, so what do we got? Last problem here is, oops, sorry. All right, so concrete highway, curve of radius 70 meters is banked at a 15-degree angle. What is the maximum speed at which the... Okay, so here, the max speed we would expect to be... This is very similar to the problem we had before, except we have a tighter radius of curvature. So that means the requirements are going to be a little higher, actually. But we're banked, so we expect that to help. All right. So having that radius, though, being smaller, means you're going to have to provide a larger acceleration. That means the max static friction is not going to be quite as high. So anyway, so free body diagram is on the left here. Again, do not tilt the coordinate system. Gravity's down, normal force is at that angle. The angle is your bank angle, and the max static friction is below the r-axis at an angle as well. So again, fastest we can go without sliding, so we're going to put our max static friction in there. So we look at our z direction and r direction components, right? And so there's a lot going on with this problem here because we have these two things at an angle, and so this makes the math a little more challenging. Not really hard by any means, but still just more terms and things like that. So in the z direction, we got our component of normal force upward. We use the cosine for that. We have a component of static friction is downward, right? So there's a negative there. And we need the sine function because that's the side opposite is the z component of that. And then minus mg, that equals 0. We're not accelerating in the z direction. We have a component of normal force that uses the sine function. That's the r component. Max static friction with the cosine component. They're all positive because I've chose left to be positive. That equals mv squared over r. So again, you got to solve this system here. It's kind of a system's kind of there's a lot going on with the system here. So all your max static frictions change to mu sub Sn, right? So what you're going to want to do here is in the z equation, you want to substitute mu sub Sn into here, and then you want to solve for n. And so you got to factor out these two terms here and move the mg over and divide. You end up getting this down here, mg cosine theta minus mu s sine theta. That's what you will get out of the z equation, which then plugs into the both places that n occurs in the r equation. It occurs obviously here, and this is mu sub Sn, the max static friction. You got to plug it in both there, or that actually might be more wise is to factor out the n, and so you have to only plug it in the one place. Put all your numbers in. You should get a speed of 34 meters per second, which is a little higher than the number we had before. And you think it'd be much higher, but remember, this is a 70-meter banked curved here, not 100. And then with the bank, though, so these two factors combined, the tighter radius and the bank angle actually allows us to go a little bit faster. So, I mean, you've seen this on freeways. There's two places this shows up a lot, right? You see a freeway, like the, I mean, if you know what I'm talking about here, the exit on the 14 when you're heading south, right? Yeah, you're heading south and you're exiting on I, right by the Jayhawk Stadium. They have this crazy bank curve there. Now, when you get off, it's just like this huge turn, and it's banked pretty heavily, actually. It's because the turn radius is really tight. And so they know that, when people get off the freeway, they're going to be traveling faster than they ought to, and so they're preventing a lot of accidents from people not slowing down enough, right? Also, you see this, of course, in like racetracks and things like that. The curves are banked so they can, maintain their motion with the fast speeds that they have. Okay, so this takes us to the end, I believe, of this. Yes, it does. And let's look at the homework here. Okay. So in the homework, we got a combination of all these things here. So for number 1, these ropes have mass. So you need to draw 4 free body diagrams, number 1. Right? Block A, Block B, rope 1, rope 2. One thing you can do to help with the problem here is if you want to figure out what this force F is up here, you actually can make a free body diagram of the entire system. So if you just imagine that this whole stuff's in like a box or something, the force is going to be accelerating like 2.5 kilograms. upward. And so you can figure out the forces based on that. So you just treat this whole thing as one system just to figure out what F is. But then you want to do free body diagrams for all the other objects and then work out what the things are here. So for part A, just say that F is pushing 2.5 kilograms upward, and then you find your F from that. Okay, 2 is a very, very great problem. Really good problem. Oh my gosh, it involves like so many things that we've discussed up to this point. Blocks stacked on top of a block. There's no forces between the blocks and the ground. There's tension back here in kilogram 1. You're gonna have so much fun with this one. I'll give you more if you email me. But this is a very important problem. If you solve this one and you really understand what you're doing, you're really ahead of the game here. And if you can't, well, you're learning physics, so that's fine. All right, number 3 here. We got a lot of tensions, all kind of tension. We're trying to rank them all here. So what you probably should do is, start from somewhere like, block M here, maybe start up here at tension 4, because you see tension 4 supporting everything here. Okay, we know the mass of this block. We know the mass of that block. We can figure out, what tension 1 is, and then we distribute that to these and so on. So realize that tension 2 and tension 5, that's one continuous rope here, right? So one continuous rope means one continuous tension. So. And what's the rest of it here? Well, the other ones are just circular motion stuff. For this number 5 here, this one's going to be solved pretty much identically to what I just showed you in the lecture here. You're going to have to change that speed to SI, all right? But you're just solving for the angle here. You already have the speed. So you're pretty much doing what we did in another problem, just solving for a different quantity there. So. And 4 and 6 are very similar circular motion things. You actually shouldn't have too much of an issue with those, obviously, but if you do, let me know. And I think that's it. So this is going to be the last video for a little while, because technically at the end of this week, we're going to have 2 non-instructional weeks. There'll be homework obviously due during that time, but I will not be posting any videos or anything else. I'm still going to communicate with the class. You can ask me questions about things. Things are going to be due next week. But we'll be taking a bit of a break after that, and hopefully everything will